going to talk about the Frauchiger Renner Gedanken experiment, a flaw in a famous paper. That's the title of the talk. And there's no reference yet, but soon an article will be uploaded to the archive. There's a reason why there's no article on the archive yet. I left City College in 2000 and then worked for Slack for 6 months and Lawrence Berkeley Laboratory for another 3.5 years. Then in 2004, I retired from physics. So currently I'm not associated with any physics department or any institution, and I have nobody to discuss my research that I've been doing during the past few years in the foundations of quantum mechanics. So I decided to give you a presentation of this work as a means to get some feedback. So this talk is in some sense a testing ground. In 2018, Daniel Frauchiger and Renner published an article in Nature Communications that addressed whether quantum mechanics can describe itself. More specifically, they considered whether quantum mechanics can govern complex macroscopic agents. And by that, I mean things like human experimentalists and their equipment. They constructed an interesting Gedanken experiment that generated a contradiction when 3 very reasonable assumptions about quantum mechanics were made. And from this Gedanken experiment, they concluded that quantum mechanics cannot be extrapolated to complex systems, at least not in a straightforward manner. This last statement is a very strong one, basically saying that quantum theory is inadequate in some respect. Quantum mechanics and extension quantum field theory have been amazingly successful. So this publication represents a serious attack on the foundations of quantum mechanics. So Nature Communications is one of the most highly regarded peer-reviewed journals in science. It has an impact factor of 5. And for reference purposes, the most desirable publication in our field is Physical Review Letters, and its impact factor is about 9. So the publication, it's not surprising that the Frauchiger-Renner publication attracted a lot of interest. Indeed, the results were cited in the popular magazine Scientific American in 2020, and they're already present in Wikipedia. However, there might be hidden assumptions in the analysis. Indeed, Frauchiger and Renner admitted this, saying in their paper, any no-go result is phrased within a particular framework that comes with a set of built-in assumptions. Hence, it's always possible that a theory evades the conclusions of the no-go result by not fulfilling these implicit assumptions. I will show in this presentation that in unitary quantum mechanics, the 3 Frauchiger-Renner assumptions are satisfied, but an additional important assumption was overlooked. I shall also argue that this assumption should not be respected in quantum mechanics. In other words, the analysis leading to this statement, quantum theory cannot consistently describe the use of itself, is flawed.
Can I ask a quick question before you go on?
Sure.
Is decoherence going to enter your discussion or theirs?
No, but I'll mention it just one little spot here.
Okay, thank you.
Okay, so here are the 3 assumptions. Assumption Q says the probability of an outcome of a measurement is given by the Born rule. Assumption C is that if one agent comes to a conclusion about a statement or prediction, then another agent, when using the same theory, assumptions, and information, will come to the same conclusion. And assumption S is if an agent is certain of the outcome of a measurement or statement, then the agent cannot conclude something contradictory it. Q stands for quantum mechanics, C stands for consistency, and S stands for single outcome. Assumption S means that an agent cannot conclude, for example, that a spin 1/2 object has a spin up with probability of 100%, and has it spin down with 100%. If an agent concludes that an object definitely has its spin up, then the agent cannot conclude that the probability that its spin is down is anything but 0. You'll see how this works later on. So I mentioned unitary quantum mechanics above. Here's its definition. In unitary, measurement does not involve wave function collapse. Wave function collapse violates unitarity in quantum mechanics. So secondly, probabilities are related to the absolute square of the wave function, which is the Born rule. Linearity and unitarity are strictly maintained even during a measuring process. There is a single universal wave function. Note that one does not assign worlds to certain linear superpositions of the wave function. Instead, the quantum mechanical interpretation of a situation is obtained by examining the wave function itself. You should already be familiar with the above because of the colloquium that I gave here last August, in which I showed that the infamous measure problem is resolved in unitary quantum mechanics. If you missed that colloquium, it's available on YouTube. Okay. Let me remind you how measurement works in unitary quantum mechanics. For simplicity, we'll consider a measurement on a spin 1/2 object. So let A be an agent who is about to measure the spin. The word agent, as I said before, includes the experimentalist in any equipment. Let psi superscript A be the agent's wave function before the measurement takes place. There are two cases. The first case is that the initial state is not a superposition of either an upspin or a downspin. It's either one or the other up to an overall phase, but it is not known which of these two possibilities is happening. The second case is when the initial state of the object to be measured is a superposition of up and down spin. That is, the spin part of the wave function is just a linear combination of up and down spin, where the sum of the coefficients, the sum of the squares of the coefficient equal 1. Here's case 1. If the initial state is either up or down, then we have the following. If it's up, then when the wave function for the agent measures the spin to be up, this is before the measurement's made, it will lead to a final wave function in which involves the agent and the concept that the spin is up. If the spin is down, then the final wave function will be the wave function for the agent and the recording of the spin being down. So here, these two final wave functions, the one for the agent with a spin up and the one for the agent with a spin down, involve the quantum constituents of the agent and possibly the spin if the spin is not destroyed. It could be that, for example, a measurement of the polarization of a photon, in which case if the photon was destroyed, it wouldn't be present as one of the quantum degrees of freedom in these two wave functions. On the other hand, if it's involves the spin of an electron, it would be. In these schematic equations, the left-hand side, respectively, the right-hand side is the wave function before, respectively, after the measurement is made. Now, in the second case, the initial wave function is a linear combination of up and down spin. And in this case, when the initial wave function is the wave function for the agent times the initial wave function for the spin, the final wave function will be a linear combination of the agent recording the spin up and the agent recording the spin down with the same coefficients as those of the spin, which follows from the second equation here, follows from the first case and linearity. So this wave function in which the agent records the spin to be up involves a configuration of the human quantum constituents that embodies the thought, I measured the spin to be up at time t, the time of the measurement, tm, and any other information, and also any recordings of the results by the machine.
Sorry, I just have a small question. Is case 1 not a special instance of case 2, or did I mix something up?
You could, yeah, it is a special case of case 1 if one of these coefficients is 0.
Okay, thank you.
Mm-hmm. But conceptually, it is actually different for reasons I don't want to go into right now, which were explained in the colloquium actually that I gave last year. Okay, now the Gedanken experiment involves Wigner-Friends, the Wigner-Friend-Gedanken experiment. So I'm going to explain that, what that is. So in a Wigner-Friend-Gedanken experiment involves an experimentalist who is Wigner's friend and Wigner himself. So an experimentalist who is Wigner's friend carries out a measurement inside a confined isolated system, for example, in a large box or in a room, an isolated room. And Wigner then performs a measurement on the entire system, that is both on his friend, the friend's equipment, and any objects in the box being measured. If one believes that measurement is associated with wave function collapse, then this thought experiment leads to conceptual difficulties. If the friend makes a measurement involving one basis and Wigner makes a measurement involving a different basis, then from the point of view of the friend inside the box, the wave function collapse should lead to one state. But from Wigner's point of view, outside the box, wave function collapse should lead to a different state. And I'll illustrate this very shortly. If quantum mechanics governs everything, then Wigner's measurement should not depend on whether the measurement has been made inside the box or not.
Stuart, just to clarify, the friend who is inside the box uses a basis of the quantum system that he or she measures, right?
Yes.
So the state in the Hilbert space of the measured object. Wigner, or the guy outside of the box, uses a basis in the total state that includes the observer who is inside the box, right? So the two of them do not use the same Hilbert space. So the statement that one uses one basis, the other a different basis, what exactly does it mean since they refer to different Hilbert spaces? One is bigger than the other.
Well, from the point of view of the universal wave function, there's no issue. And I'll illustrate that very shortly. Okay.
So the Wigner friend has some basis which is by tensor the states of the experiment of the Schrödinger's cat and his own state, presumably, right? Something like
I'm going to show this in the very next slide. You'll see both these questions will be answered in the next slide. So I actually, in the colloquium I gave here last August, I actually secretly provided you with this Gedanken experiment for this case when I discussed Schrödinger cats. I actually renamed these things here when I gave the colloquium, calling this Wigner's dog and Schrödinger's cat. So this cartoon's probably familiar to some of you that attended that colloquium. So I'm going to be specific. I'm going to consider the case of spin 1/2 measurements. And this is what is involved in the Frauchiger Renner experiment. So this is what happens in unitary quantum mechanics. So the initial wave function involves the wave function for Wigner, the wave function for the friend, the Wigner agent, the wave function for the friend agent, and in general have a linear combination of up and down spin. So after the friend performs the measurement of the wave function, then the wave function will become this. So this is just using what I showed a few transparencies ago, a linear combination of the friend inside the box measuring the spin to be up, and a final wave function for the agent friend in which the spin is measured down. Suppose Wigner performs a measurement to determine whether the box is in one of two states. And this is not the most general situation, but this is the one that we're going to need. So there's a plus state, which involves the sum of the wave functions for the two agents, the final wave functions for the two agents, one being up and down, or minus being the difference of the two wave functions. Then the initial state, which became this after the friend made the measurement, will become a linear combination of these two plus and minus states. So the Wigner agent will have a certain probability of measuring the system inside the box to be plus, or a certain probability that he measures it to be minus. The absolute value of A squared being the probability of the first case, and the absolute value of B squared being the probability that measures it to be minus. Here I'm just using these definitions. If it was a pure plus state, then Wigner would obtain the Wigner agent wave function would be this. And actually the coefficients A and B are easy to compute from this. They're just actually the sum and difference of these A and B coefficients. So in unitary quantum mechanics, there's no problem. This is what happens. There's no ambiguity in the final wave function. It's this term right here. If wave function collapse is supposed to happen, then from the friend's point of view, the wave function at this stage collapses to either this term or this term. It collapses to either this or this, with probability absolute value of A squared or probability absolute value of B squared. But from Wigner's point of view, if there was wave function collapse, it should collapse to either this plus wave function or this minus wave function with probabilities involving the absolute value squares of A prime and B squared prime. These states are incompatible, and these probabilities actually don't agree. So this Wigner-Friend Gedanken experiment was contrived to show that wave function collapse cannot occur. For the Frauchiger-Renner case, we need the case when the spin is either up or its spin is down. So, so if the spin is up, then the final, so if the spin is just up, then you can express plus and minus in terms of that basis. It's the sum. And so one gets, in this case, that the final wave function will be just the sum of the plus and minus cases. So the key, and if the spin is down, then using the fact that you can express the wave function for, this actually should be W times this. There's a little error here. Whoops. Let's see. Well, anyway, there should be a W multiplying this as it is here. Then one gets that the final wave function will be the difference of the plus and minus states. Just follows from re-expressing the basis in two different bases, one involving upspin and downspin, and the other involving the plus and minus. Basically, if the spin is up, then you'll get the sum of the plus and minus states. And if the spin is down, then you'll get the difference of the plus and minus states. So now I come to the Frauchiger-Renner Gedanken experiment. This thought experiment involves two spin 1/2 objects and two sets of Wigner friends. And we'll distinguish the two different spin 1/2 objects and the agents using the colors brown and purple. So this is what the initial state is. It involves entangled spins. It involves the brown spin being up times the brown spin being down, the brown spin being down, and then the purple spin being up, the brown spin being down, and the purple spin being down, each with equal probability. And then we have a brown Wigner agent and a brown Wigner friend who's going to measure brown spin, and a purple Wigner agent and a purple Wigner friend that's going to measure purple spin. Now, all the agents are told in advance that the spin part of the initial state is this particular entangled combination. And they are also told the entire experimental procedure. That is, which agent will measure which state at which time. There are 4 steps involved. 2 measurements by friend agents, followed by 2 measurements by Wigner agents. So in the first step, brown agent F measures the brown spin at time t1, t1 being the time of the measurement. The wave function becomes, and you just bring it in here, and so the first term becomes this. The brown agent friend measures the spin to be up and gets this as the final wave function, or in the second 2 terms, the brown friend agent measures it to be down. In the second step, the purple agent measures the purple spin at time t2. The wave function then becomes, it's the same thing. The agent measures it to be down in this case, then up in this case, and then down in this case. So after the first 2 steps, the wave function has the following form. So here I've written it again. This is the wave function after the 2 friends have measured the spins at time t2. In the third step, the brown Wigner agent makes a measurement at time t3 on his friend in the plus minus basis. Remember, it involves the plus state involves the sum of the 2 wave functions, and the minus state involves the difference. And the wave function becomes, and remember the rule, if it's up, it becomes the sum of the plus and minus. If it's down, it becomes the difference. And so after step 3, this is the wave function. So in the final step, so I've written the wave function now after time 3. In the 4th step, the purple agent, Wigner agent, makes a similar measurement at time 4 on his friend, again in the plus minus basis. So the wave function, this is down, this is plus, there's that term. This is down, so we get the minus. There's the minus there. This is up, so we get the plus. This is that term, and this is down, so we get the minus. So this is the wave function at time t4. And you can rearrange these terms. You see the plus terms all contribute. Plus, plus, we have a plus, plus, and a plus, plus, so we get a 3. But the plus and minus terms have a cancellation. For example, minus plus, this comes with a plus, but minus plus here comes with a minus, and then minus plus comes with a minus, so we get a minus overall. And it works the same way for the other. So this completes the procedure for the Gedanken experiment. So are there any questions at this point?
Just a small remark, totally trivial. The normalization is wrong. You also need a square root of 3, but that's completely irrelevant. Don't worry about it.
No, I actually did this deliberately so I wouldn't have a lot of factors of, let me find out where it is. Yeah, I didn't put in a 1 over square root of 3 here, just so I would avoid a lot of, make the transparencies easy. What you can do is you just put it in the normalization of one of these.
That's okay. Normalization is not relevant. It's not going to change.
Yeah. So, okay. So there are 4 statements that Frauchiger Renner derive, and here they are. Statement 1 says, if at time t4, purple agent W and brown agent W respectively obtain minus measurements, then purple agent W obtained a minus measurement at time t4, and brown agent W obtained minus at time t3. The second statement says, if brown agent W obtained minus at time 3, then purple agent F obtained a measurement of up at time t2. The third statement is that if purple agent F obtained a measurement of up at time t2, then brown agent F obtained a measurement down at time t1. And the fourth statement is if brown agent F obtained a measurement of the brown spin being down at time t1, then purple agent W will obtain a measurement of plus at time t4. Notice these are completely linked. The conclusion of this one leads into the next statement. So here it concludes that brown agent measured minus, and if he measured minus, purple agent F measured up, if purple agent measured up, brown agent measured down. So combining all these statements, one starts out with the first premise here. If at time t4, agent W and agent Brown obtain measurements of minus and minus, then agent W will obtain a measurement of plus at time t4, which is a contradiction. And I call this the contradictory statement. So now here's where assumption S comes into play. It says that if an agent is certain about the outcome of a measurement or statement, then the agent cannot conclude something contradicting it. And this is used in the contradictory statement because the contradictory statement says that agent W will measure the state to be both minus and plus at time t4. Assumption C, which says that if one agent comes to a conclusion about a statement or prediction, then another agent, when using the same theory, assumptions, and information, will come to the same conclusions, is also used because agent W has to know about statements 2, 3, and 4. He was not involved in those measurements. However, because he knows the initial state and the experimental procedure, he can deduce them. So agent W directly measured the state to be minus, but deduced that he should measure it to be plus from the measurements of the other agents. So now I'm going to go through the derivations of these statements. Actually, statement 1 is obvious because there was a term in the wave function involving minus minus. So the wave function at t4 contained this term, and agent W4 made the measurement at time t3. The purple Wigner agent made it at time t4. So if at time t4, agent W and purple agent W and brown agent W respectively obtained minus and minus, then purple agent W had to obtain minus at t4, and brown agent W had to obtain minus at t3. That's completely trivial. Now the next three are a little trickier. I'm going to jump to statement 4. If the friend agent, brown agent F, obtained a measurement of down at time t1, then purple agent W will obtain a measurement of plus at time t4. So statement 4 involves the second and third components of the wave function, because the wave function at time t1 was given by this. And if you notice, the second and third terms involve the brown agent F measuring the spin to be down. So when I showed you the wave functions at times 2, 3, and 4, they were in the same order. So I kept this, I kept the 3 terms separate. So we just have to look at the wave function at time 4 involving the second and third terms. So, and actually we can see what this is up. So it's got to be this is down. So it's got to involve the minus, and this was up. So it's got to involve the plus. This was down. So it's got to involve the minus, and this was down. So it has to involve the minus. And if you notice here, let's see. So the claim is that this is proportional to the plus term. And what happens there, if you look at the minus term here, it multiplies this, and the minus term here multiplies the same thing, but this is plus and this is minus. So these cancel and you're only left with the plus term. So the final wave function is proportional to plus. Here's a simpler way of actually seeing it. Note that since the down term involves something involving the sum of these two, agent W, when he performs the measurement, will have to get something proportional to plus. Okay, now let's go to the second statement. It says if agent W obtained minus at time t3, then purple agent F obtained a measurement of up at time t2. Now, statement 2 involves the second component of the wave function, because if you look at, we're talking about purple agent F obtaining a result of up, and the first and third terms involve downspin. So it involves this middle term here. Now, at time 2, that middle term involved this term here. So that means if brown agent okay, so I'm sorry. So if we look here, if brown agent has a minus, oh yeah, the way it works here is you see this term and this term cancel, right? This term and this term cancel. So so it only involves this middle term, and this middle term actually only involves upspin at time t2. So if the agent obtained minus at time t3, then agent F had to obtain up because these two terms cancel. Now the third statement, if purple agent F obtained up a measurement at time t2, then brown agent obtained a measurement of down at time t1. And that happens here because you see the only term at time t2 that where the brown agent is measuring the spin be down is coupled to the purple spin being up. So we've actually derived all 4 statements. So So maybe you didn't follow just in case you didn't follow the math, here's roughly what's going on. In the Frauchiger, Renner, Gedanken experiment, 4 measurements are made in 4 steps, are carried out for an entangled system involving 2 spin-one objects. The first 2 steps involve straightforward measurements of whether the spin was up or down. The next 2 steps involved Wigner-friend measurements in which a Wigner agent performed a measurement on his corresponding friend. 4 logical statements are attained, and when combined, they yield the contradictory statement, which is, if at time t4, purple agent W and brown agent W respectively obtain minus and minus, then purple agent W will obtain a measurement of plus at time t4, but purple agent W obtained a minus at time t4. From this, Frauchiger, Renner concluded that quantum mechanics cannot always consistently describe itself.
I'm a little confused. You have 3 purple agents W and one brown purple agent W. Shouldn't it be 2 of each, or is that?
No, there's 1 purple W agent, 1 brown W agent, 1 purple friend, and 1 brown friend.
Right, but I'm looking at your statement on the slide. Should one of those?
It's the same agent. This is the same agent.
Should one of the purples be a brown?
No. No.
That's supposed contradiction, Peter, that the same agent W would
Same
get
agent.
one and the other.
Yeah.
Okay, that's the contradiction. It's the last phrase.
Yes. I mean,
Okay.
this is unbelievable, right? It
Yeah.
is saying that purple agent W should get 2 completely opposite measurements.
Right. Okay. Okay. I see that. It was just. All right.
No, good. I'm glad. I actually wanted to pause here anyway to see if there were questions.
I do have a question, maybe kind of just kind of what the rules are. So you're not doing wave function collapse here, right? These
Exactly. And I'm using unitary quantum mechanics in which wave function collapse is not allowed.
Okay, good. So then I guess my question is, what's the rule for applying the Born rule? So if I want to say know what happened at time t2, should I just look at the entire wave function at time t2 and apply the Born rule to that wave?
Yes. So let's look at it. Here it is at time t2. There should be a 1 over the square root of 3 in here, but the coefficient is 1 over the square root of 3. So there's a third of a chance of having this case in which the brown friend measures it to be up and the purple friend measures it to be down. It's just, the probability is the square of the coefficient, which is 1/3. There's 1/3 of obtaining down and then up, and there's 1/3 obtaining down and down. That's how the Born rule works.
Okay, and does that lead to the same kind of 4 correlations that you found?
I'm not doing the analysis for the wave function collapse case, and according to Frauchiger Renner, it violates one of the three assumptions, and so you don't generate a contradictory statement. What's here is actually all 3 of those reasonable assumptions are satisfied here. We're going to see very shortly that there was a hidden assumption that they have made that invalidates this contradictory statement. So the interesting part is coming up. So after reading the Frauchiger Renner publication, and probably many of you feel this right now, I had the feeling that something was not right. There were others who claim the Frauchiger-Renner result was not correct, but I didn't find their arguments convincing. And for example, one paper claimed that decoherence invalidated the analysis, but I didn't understand why. And anyway, so here were some of the initial possibilities that I thought might be problems. One involved timing. The measurements take place at different times, but to generate the contrary statement, the 4 statements need to occur at the same time. You know, you can't have something true at one time that may be false later or so forth. But this really doesn't turn out to be a problem because of assumption C, this consistency assumption, because the purple, I think it was the purple agent W, Wigner agent, is able to deduce all those other statements at time T4 for himself. Another thing was, I thought it might be related to self-referring statements. Perhaps the system generated a logical contradiction through a set of statements that simply refer to themselves. For example, in English, we can have one statement that says statement 2 is true, and then we have a second statement that says statement 1 is false. And if you combine these 2 statements, then you get a contradiction, namely that statement 1 has to be both true and false. If it's true, then using statement 2, it's false. And if it's false, then statement 2 says it's true. This would not be a fundamental problem for quantum mechanics, in my opinion, just an issue of semantics. Another possibility is that Wigner-Friend experiments are not even possible theoretically. I actually have a discussion of this in Appendix A, entitled Some Comments About Wigner Measurements, in the paper that I shall post on the archive. So there's issues with the logic in the Frauchiger-Renner experiment. To arrive,
Stuart, can I ask a question?
sure.
Referring to the statement that Wigner-Friend experiments are not possible, even theoretically, can you actually elaborate on that a bit? I mean, I find it, you know, I mean, the way I would think about this is, forget quantum mechanics, everything has to be phrased within a field theory framework. And if you like, relativistic field theory framework. And how do you even pose the question of Wigner-Friend there? Is that the issue that you're talking about?
Well, I don't think there is any problem theoretically. I mean, what happens in the box is, say, governed by quantum field theory, right?
Yeah, but the box and the outside world are all connected by quantum field theory.
Right, but what happens is, before Wigner makes the measurement,
The point I'm trying to make is, you know, wave functions don't factorize once you have the field theory situation, right?
well, no, they do before they interact. So it represents, before Wigner makes his measurement, it's a non-interacting system.
I don't even know what that means in field theory. I mean, there is a wave.
Well,
There is a wave function that refers to all the fields that you have available, and that doesn't factorize into something inside the box and something outside the box, right?
well, what happens is, if Wigner can't be in contact with a friend before the experiment is done. If they came in contact initially, then there's a problem. We could discuss this later, but in quantum mechanics, it's quite clear when you mean 2 systems are independent.
I think personally, to add here that I believe parameter.
Wait a second, I haven't finished saying what I was saying. So in quantum mechanics, mathematically, it's when the 2 wave functions factorize, that then they're independent. In quantum field theory, I actually haven't thought about this, but presumably there's an analogous thing. There's situations in which you construct your Fock space and you look at wave functions, and at a certain point in time, the wave functions factorize. For example, I mean, you could look at something very far away, a planet that's a million light years away, has a wave function involved with all the constituents there. And then we have what's going on here on Earth. And I mean, the two wave functions are going to factorize in field theory as well. Okay, now someone else want to say something?
All I wanted to say is that I believe Paramessoron's question or other objection may be valid, that in quantum field theory, you do not have strict factorization. It's just that for this particular situation, I don't think it will turn out to be relevant. I mean, if we decide that you cannot have factorizable wave functions, then none of that is true. But we can assume that you have, at least in this non-relativistic setting, and even approximately. And then there is still a flow to the Renner argument that Stuart is going to tell us, and I will tell you what I think afterwards.
Okay, Alexei, thanks.
Okay, so we'll continue. In any case, they did this within the context of quantum mechanics, but I think a lot of the things I've been discussing, both in the colloquiums and in this talk, are interesting to think about from the field theory point of view too. So here I come to the crux of the problem. Issues with the logic in the Frauchiger-Renner argument. So to arrive at the contradictory statement, four logical statements had to be combined using the transitive rule of logic. Recall this says if A implies B and B implies C, then A implies C, which is written logically in this form. And here's a Venn diagram. If something is in A, then it has to be in B, so A implies B. If something is in B, then it has to be in C. And since A is in B, it also has to be in C. So that's the Venn diagram representation of this logic. It turns out that the transitive rule of logic does not apply to statements about wave functions and measurements. I mean, this seems, I mean, we're so used to using the transitive rule of logic. How could this even be? But in fact, this is what's going on here. So let me consider the use of the transitive rule to combine statements 3 and 4. So I'm going to let A be the statement. Purple agent F obtained a measurement of purple spin being up at time t2. We're going to let B be that brown agent F obtained a measurement of brown spin down at time t1. And we're going to let C stand for the statement of proposition that purple agent W will obtain a measurement of plus at time t4. So these A, B, and C represent the A, B, and C in the previous slide. So statement 3 is A implies B, if you look back at what I showed you before. And statement 4 is B implies C. So transitivity should imply that A implies C, but this is not true. So let's see what's going on here. So let's look. A was agent F obtained up at time t4. So that's this middle term here. And that implied that agent F obtained down at time t1 when brown agent F measured it to be down. Then agent F will obtain a measurement of plus at time t4. Well, that involved, well, B implies C involved brown agent F measuring the spin to be down at time t1, but there are two terms here. And those two terms led to the cancellation of the minus part. And that's how it ended up being that purple agent W will obtain plus. But notice that we started with the middle term. A, the premise, purple agent F obtained up at time t2 only involves the middle term. And that term will evolve to the middle term at time t4, which involves all four possibilities. It will involve minus and minus as well as the other three terms. When these second and third terms are combined, the minus and minuses cancel. So the reason for the violation is that statement 4 needs a cancellation, or you can consider it as a quantum interference effect between the second and third terms to cancel out the minus result, leaving only the plus result. But statement 3 eliminates the interference by restricting the statement to the second term. Okay, so maybe I'll give people a chance to ask any questions here. Okay, so it turns out that statements 2 and 3 also can't be combined using transitivity, but statements 2 and statement 3 can be combined using transitivity, but statements 1 and 2 cannot. So if the four statements cannot be combined using the transitivity rule of logic, then the contradictory statement cannot be generated. So this is a major problem in the Frauchiger Renner paper. So the following is a simple example of the violation of the transitivity rule for logic, for statements about wave functions. So we don't even have to use different times here. Consider the spin part of the initial wave function at time t0. This is the same spin wave function, entangled spin wave function we've been considering. This wave function can be written, okay, and here z indicates that the spin is being done in the spin quantization is in the z direction. It can also be written involving these second two terms are the sum of up and down spin in the z direction, which is proportional to up spin in the x when spin is quantized in the x direction. So this wave function here can be also written as this. So let A be the purple spin is up in this in the z quantization case, and that the brown spin is down, and the purple spin is up in the x direction. Then the first term's not going to play a role here, but A implies B is true, because if the purple spin is up, then the brown spin has to be down in the z direction. And B implies C, because if the brown spin is down, then the purple spin has to be up in the x direction. So if A implies B and B implies C, and you could use the transitivity property of logic, you would conclude that A implies C, which is that A was the purple spin is up in the z direction. You would then conclude that the purple spin is up in the x direction, which is obviously false. In fact, there's a one-to-one correspondence between spin 1/2 objects being measured in the z and x direction and the states of the Frauchiger Renner Gedanken experiment. Just the up and down spins, we can think of being real spin 1/2 objects in the up and down z direction. In fact, that was the starting point anyway. And the plus and minus, which involved this, in some sense, a measurement on the sum of these or the difference of these, can be considered as up and down spin in the x direction. And this is consistent. This corresponds, as I said, because plus involved the sum of the Wigner-Friend measurements in up and down directions, which would correspond to up and down spin, which is up spin in the x direction, and minus works the same way. So actually, starting with this spin wave function, one can obtain the analogs of statements 1 and 4 at time t equals 0. If brown and purple spins are down, then the Brown spin must be down. If the Brown spin is down in the X direction, if the Brown spin is down in the X direction, then the purple spin must be up in the Z direction. If the purple spin is up in the Z direction, the Brown spin must be down in the Z direction. If the Brown spin is down in the Z direction, the purple spin is up in the X direction. So you start out the purple spin is down in the X direction and you end up being up. So if one were allowed to use the transitivity rule of logic, then one would conclude would obtain the analog of the contradictory statement. If brown and purple spins start out as being both down in the X direction, then the purple spin must be up in the X direction. You just can't apply the transitivity to statements about wave functions. So in their work, Frauchiger and Renner concluded that quantum field theory cannot be extrapolated to complex systems in a straightforward manner. A contradictory statement for unitary quantum mechanics arises only if assumption S is replaced by a stronger assumption L. L stands for logic here, which says that statements by agents concerning measurements of wave functions can be combined using the standard rules of logic. However, once one understands that statements about wave functions sometimes should violate the transitive property of logic, there's nothing in principle ruling out unitary quantum mechanics being able to govern complex and microscopic systems. We don't know whether this is true. Many of us believe it to be true, but this paper does not rule out this possibility. Furthermore, unitary quantum field theory, the generalization of unitary quantum mechanics to include second quantized processes, does not have a quantum measurement problem. As I mentioned before, this is the result that I presented here at City College in the colloquium last August, and that's available on the physics department's YouTube channel. Nor does it have an Einstein-Podolsky-Rosen paradox, a result that I presented at City College in a colloquium in November of 2019. And both these results are available on the archive in a paper entitled On Wave Function Collapse, the Einstein-Podolsky-Rosen paradox and measurement in quantum mechanics and field theory. So to conclude, although quantum mechanics can appear to be puzzling at times, the major conundrums have been resolved. Thank you.
Okay, let's thank Stuart.